Welcome back from Easter break. I missed you guys. I wanted to make sure I gave you an update on the latest that you can expect for the rest of these next 2 weeks before finals week, and then give you an update on the topics that will be covered for your finals review starting next week as well. So, first thing you guys should know is that starting next week, I will begin the finals review. So, just make sure I write this down. Finals review will start next week. Okay. So I will be sure to give you guys a lecture going over the types of things you should understand for your final and the types of content you should be on the lookout for with these remaining lectures. So that will be next week. I think I will post that next Tuesday for you guys so you can stay up to date on that. Okay. But other than that, the topics we need to finish for the course are Laplace transforms, and also linear algebra and its integration with differential equations. You would be surprised just how simple it's going to seem, how you can connect the two topics very easily. So you're going to see that discussion on this Thursday and next Tuesday with a wrap up on Thursday. So you can see how all of it comes together to solve systems of any dimension, of any size, using linear algebra and differential equations. Okay. So that's a tall order, and that's coming this week and next week. So the question I usually am asked as well by students is, will the content that I'm discussing this week and next week be on the finals? The answer is yes. It will be on the final. It won't be complicated though. It will be no more difficult than your homework assignment that I'll be posting later today, with today being Monday, um, the 13th of April. So I'll just make sure that you guys have that homework assignment, and that also I would encourage you to go ahead and begin this second half of this homework assignment in addition to the first part of homework 5. I try to get everything done by next Friday, the 24th, I believe. I'm just checking my calendar to make sure. That's what I have here. Yes, that'll be the 24th. So make sure you have all that done by the 24th, part 1 and part 2 of homework 5. Okay? So let's go ahead and get started. I want you guys to begin to understand the concept behind Laplace transforms. I did provide you guys a little bit of an introduction with the Khan Academy videos last Thursday, but I want to give you the in-depth scoop, kind of like the inside understanding of how these things come about and why they're used, and then how we can use them in our own differential equations in solving those systems. Okay? So first of all, I want to begin by saying it's always just a little scary when you devote a whole section just to define something. So Laplace transforms, or just transforms as they're sometimes called, can seem scary when we first start looking at them. But you'll see that they aren't really as bad as they first appear to be. So before we get started with the definition of a Laplace transform, we need to get another definition out of the way. So first of all, I want you guys to remember what a piecewise continuous function is. Okay, so let me go ahead and write this out. So definition, a function, okay, a function is called, okay, piecewise continuous, piecewise continuous, or CONT for short, on an interval, sorry, let me spell that a little differently, on an interval, okay, if the interval, okay, so if the interval can be broken, into a finite number of subintervals okay, on which the function is continuous, or CONT, on each open subinterval okay, that is the subinterval without its endpoints, and has a finite limit okay, a finite limit at the endpoints at the endpoints of each subinterval. Phew, right? So we're going to sketch what this looks like. But let me go ahead and just restate the definition and then explain it as we make our sketch. So a function is called piecewise continuous, okay? Piecewise continuous on an interval if the interval can be broken into a finite number, not infinite, a certain number of subintervals, that is smaller intervals on the real line, by the way, we're talking about real numbers only, on which the function is continuous on each open subinterval and has a finite limit at the endpoints of each subinterval. Okay, so let's go ahead and draw an example of what this looks like. I'm going to give you a piecewise continuous function on an interval. Okay, and the interval, of course, is just going to be the real line in this case. We're talking about real numbers on the x and y axis, so this would be R2 in this case. So here we have some point that's defined on the interval, right? And then we have some point that's undefined on the interval, okay? So at this point, if it was just this, then this would not be defined as a piecewise continuous function on an interval. However, if I add a point that is defined here and another open point here, then it becomes defined because the limit exists at the two endpoints. Okay? And then if I was to continue the function in this fashion, it's still defined because the limits at both of these endpoints, and these are the endpoints I'm talking about, here, here, and here, they're still defined. And you could see that the function that is being drawn to connect these endpoints is continuous. Okay? Um, Continuity, by the way, doesn't imply it's differentiable, right? So here we have a jagged edge that's non-differentiable, but it's still continuous, okay? And then up here, we have a point that is not defined, but it's still defined on the endpoint, since there is a point here that's defined. And this goes on and on and on until we get to a point that is defined, okay? So this is an example of what we call a piecewise continuous function on an interval of the real line, okay? And it's in this space that Laplace transforms live. They don't live in any other space but this one. And you'll see why from the definition it has to be so, okay? So let's go ahead and move onward from here. In our next video, we'll show how this works. Stay tuned.